Today, we're tracking what may be the most scrutinized celestial visitor in the history of modern astronomy. And we finally have answers from NASA. After weeks of silence during a government shutdown that fueled rampant online speculation about alien spacecraft and government cover-ups, the space agency has released a comprehensive briefing on the interstellar comet designated 3I Atlas, the third confirmed object ever detected arriving from beyond our solar system. What they revealed is not a Hollywood blockbuster scenario, but something arguably more profound. A time capsule from an ancient star system, carrying chemical signatures that challenge our understanding of planetary formation, exhibiting behaviors that defy easy classification, and reminding us that the universe still holds mysteries we are only beginning to decode. This is not just another comet. This is a messenger from deep time and deep space, and the data NASA just released raises as many questions as it answers. If you want to stay updated as this story develops over the coming months, because it absolutely will, hit that subscribe button now. We are going to break down every detail from this briefing, and I promise you, the devil is in those details. Let's start with the discovery itself, because timing matters here. 3I Atlas was first spotted in July of this year by the Atlas Survey System in Hawaii, an automated sky-scanning network designed to detect near-Earth objects and potential impact threats. Within days, astronomers confirmed what they had long suspected but rarely witnessed. This object's trajectory did not originate from within our solar system. Its velocity and angle of approach told an unmistakable story. It came from interstellar space, the vast emptiness between stars, traveling for potentially millions of years before chance brought it into our cosmic neighborhood. Only two other objects have ever been confirmed with this distinction. The first was Oumuamua, discovered in 2017, a cigar-shaped enigma that sparked fierce debate about whether it was a comet, an asteroid, or something else entirely. The second was Comet 2I Borisov, identified in 2019, which looked and behaved almost exactly like comets born in our own solar system, offering reassuring familiarity. 3I Atlas, however, sits somewhere in between, familiar enough to classify, but strange enough to provoke intense scientific curiosity and, unfortunately, wild speculation. Because here is what happened during those crucial weeks after discovery. 3I Atlas was positioned on the opposite side of the Sun from Earth, making direct observation from ground-based telescopes nearly impossible. At the same time, a 43-day government shutdown began, freezing NASA's ability to release new images, issue public statements, or coordinate messaging. Into that information vacuum rushed a torrent of online rumors. A preprint paper, not peer-reviewed, authored by a trio of researchers, including Harvard astrophysicist Avi Loeb, suggested that the comet's characteristics could hint at disguised, possibly hostile, alien technology. Loeb, who had made similar claims about Oumuamua, argued that certain anomalies in the object's behavior warranted consideration of non-natural explanations. Then Elon Musk, during a podcast appearance, casually suggested that something beyond gravity might be influencing the comet's motion, a comment that ricocheted across social media. And then, in a moment that perfectly encapsulates the strange intersection of celebrity culture and scientific discourse, Kim Kardashian posted on X, tagging NASA acting administrator Sean Duffy, asking him to spill the tea on the object. That post went viral, accumulating millions of views and further amplifying public fascination. By the time NASA was able to hold its briefing last week, the narrative around 3I Atlas had spiraled far beyond the realm of sober astronomical inquiry. So NASA wasted absolutely no time. The very first statement from Associate Administrator Amit Kshatriya was blunt and unambiguous. This object is a comet. It looks and behaves like a comet, and all evidence points to it being a comet. Nikki Fox, the Associate Administrator of NASA's Science Mission Directorate, reinforced the message, stating that none of NASA's observations detected any technosignatures or anything that would lead scientists to believe this was anything other than a comet. She also emphasized, and this is crucial for public reassurance, that 3I Atlas poses zero threat to Earth. The closest it will ever come to our planet is 170 million miles, roughly 270 million kilometers, which is beyond the orbit of Mars and well outside any conceivable danger zone. This contradicts what we previously thought might be possible during the early days of speculation, when the lack of data allowed imaginations to run wild. Now we have data. Let's look closer at the data. The second major revelation from the briefing involves an unprecedented level of international and interplanetary coordination. From the moment scientists confirmed the interstellar origin of 3I Atlas, they faced a logistical nightmare. The comet was on the far side of the Sun, invisible to most Earth-based instruments. So in August, NASA convened what can only be described as a celestial all-hands-on-deck meeting, bringing together teams for more than 20 missions scattered across the solar system. Dozens of spacecraft, from Earth orbit to Mars and beyond, were tasked with observing the comet from their unique vantage points. Tom Statler, the lead scientist at NASA for Solar System Small Bodies, described the effort with a sports analogy that actually captures the complexity quite well. He likened it to watching a baseball game from different seats around the stadium. Each spacecraft had a different angle, a different distance, a different set of instruments, and together they assembled a composite picture far more detailed than any single observer could achieve. Mars, as it happened, was positioned on the favorable side of the Sun, giving NASA's Mars Reconnaissance Orbiter a front-row seat. In early October, from a distance of about 90 million miles, the orbiter captured images of 3I Atlas as a fuzzy white ball, revealing its dust and ice coma, the glowing envelope of gas and debris that surrounds the nucleus of a comet as it warms. Meanwhile, the MAVEN orbiter, also in Mars orbit, detected the comet from 20 million miles away using ultraviolet sensors that picked up hydrogen gas, released as sunlight vaporized water ice from the comet's surface. Farther out, NASA's Psyche mission, currently en route to a metal-rich asteroid in the main belt, imaged the comet from 33 million miles away in September. The Lucy mission, designed to study Jupiter's Trojan asteroids, observed 3I Atlas from the opposite direction, providing critical data that helped researchers reconstruct the three-dimensional structure of the dust tail. The Hubble Space Telescope, orbiting Earth at an altitude of just a few hundred miles, but looking across a gulf of 277 million miles, observed the comet and revealed a pear-shaped coma, a detail that allowed scientists to narrow the possible size of the nucleus to somewhere between 1,400 feet and 3.5 miles in diameter. Even the SOHO Observatory, a joint NASA-European Space Agency mission stationed between Earth and the Sun, managed to detect the faint object despite expectations that it would be too dim to register in its instruments. This is an extraordinary achievement of coordination, and it underscores how seriously the scientific community took this opportunity. Interstellar objects are vanishingly rare. We cannot afford to miss a single data point. Here is the crucial detail. This was not just about satisfying curiosity. Scientists realized that 3I Atlas offers a rare window into the composition and history of distant, older star systems. Based on the velocity of the comet when it entered our solar system, Statler explained, the circumstantial evidence points to an origin in a very old planetary system, possibly one older than our own Sun, which formed about 4.6 billion years ago. That gives me goosebumps to think about, frankly, Statler said during the briefing, and you can hear the genuine wonder in his voice. He went on to describe 3I Atlas as a new window into the makeups and histories of other solar systems, a frozen archive of conditions that existed around a distant star long before Earth even existed. Think about that for a moment. This object may carry within its ices and dust grains the chemical fingerprints of stellar environments from an era when our own solar system was not yet born. It is, in a very real sense, a time capsule from the deep past of the galaxy. So, what does this actually mean? It means that every measurement we take from 3I Atlas is not just about this one comet. It is about testing our theories of how planets and comets form in different stellar environments, how ices behave under different radiation conditions, how long objects can survive in the interstellar medium, and whether the building blocks of solar systems are fundamentally similar across the galaxy or wildly diverse. And the early chemical data from 3I Atlas suggests the latter, which brings us to the fourth revelation from NASA's briefing: intriguing chemical clues and anomalous behavior. So far, 3I Atlas has behaved exactly as a comet should as it warms near the Sun, shedding water and carbon dioxide as its ices sublimate, turning directly from solid to gas without passing through a liquid phase. But within that expected behavior, there are intriguing twists, subtle deviations from the norm that hint at a different origin story. The James Webb Space Telescope, which provided the first infrared observations of an interstellar object since its launch, detected an unusually high ratio of carbon dioxide to water ice in the comet's emissions, well above what is typical for comets born in our own solar system. That single measurement tells us something profound. It suggests that the ices in 3I Atlas were shaped by a harsher radiation environment around an older star, possibly one with a different spectral type or a different history of stellar activity. In our solar system, comets that formed in the outer regions, beyond the frost line where water ice is stable, tend to have relatively balanced ratios of water and carbon dioxide. If 3I Atlas formed in a system where the parent star emitted more ultraviolet or higher energy radiation, that could selectively destroy or alter the water ice, leaving behind a higher concentration of carbon dioxide. It is a clue written in molecules, and it points to a different cosmic environment. Scientists have also detected gas unusually rich in nickel relative to iron in the comet's emissions. This is not something we see often in local comets, and it raises questions about the metallicity of the original protoplanetary disk where 3I Atlas formed. Were the building blocks of that distant solar system enriched with heavier elements from earlier generations, of supernovae? Did the comet form closer to its parent star than typical Oort cloud objects do in our system, picking up more metallic dust? We do not know yet, but the data is there, and it is tantalizing. The dust around the comet also shows slightly atypical properties. Spectroscopic analysis suggests that the grain sizes differ from those of comets native to our solar system, possibly indicating a different formation environment or a longer exposure to interstellar radiation, which can erode and alter dust grains over millions of years. One especially curious behavior noted during the early observations was that dust was initially blown toward the sunward side of the comet before solar radiation gradually pushed it back into the more familiar tail configuration. This is a longer and less common sequence than scientists usually observe in homegrown comets, where the radiation pressure from sunlight typically dominates almost immediately. Why did 3I Atlas exhibit this delayed response? Is it related to the composition of the dust, the rotation of the nucleus, or some other factor we have not yet identified? These are the kinds of questions that drive scientific inquiry, and they remain open. But the anomalies did not stop there. Recent observations have revealed even more peculiarities that were highlighted in the NASA briefing. An image taken on November 27th by amateur astronomer Satoru Murata and subsequently analyzed by professional teams shows a spiral structure in the object's tail, rather than the straight, streamlined formation typically seen in cometary tails. This spiral pattern suggests that the nucleus is rotating and emitting jets of gas and dust in a non-uniform way, creating a corkscrew effect as the material streams away. The image also clearly shows a stable anti-tail directed toward the Sun, a phenomenon that occurs when larger dust grains, too heavy to be pushed away by radiation pressure, linger in the comet's orbital plane and appear to point sunward from certain viewing angles. And then there is the compact, bright green nucleus, glowing with the characteristic color of ionized cyanogen or diatomic carbon, molecules commonly found in cometary emissions but rarely so intensely concentrated. Even more intriguing, the image appears to show a small fragment separating from the nucleus. Is the comet fragmenting? Is this a normal outburst of activity, or is it a sign of structural instability? These observations complement earlier data from September 2025, when European telescopes recorded X-shaped intersecting jets around the object, suggesting multiple active regions on the nucleus releasing gas and dust in different directions. Additionally, 3I Atlas has exhibited a color shift from blue to emerald green and a rise in brightness, even though the object has already passed perihelion, the point in its orbit closest to the Sun, and should theoretically be cooling and dimming as it moves away. This contradicts the expected light curve for a comet, and it raises the possibility that new vents are opening on the nucleus, exposing fresh ice to sunlight, or that the composition of the ice is changing as deeper layers are revealed. Could the comet be layered with different ices at different depths, sublimating at different rates as it warms? That is certainly possible, and it would explain the evolving brightness and color. But again, we are in the realm of hypothesis, not confirmed fact. Now, let's talk about trajectory, because this is where things get particularly interesting and where the scientific debate intensifies. The fifth key point from NASA's briefing involves trajectory revisions and ongoing monitoring efforts. experts have updated the calculated trajectory of 3I Atlas, altering the predicted point of its close approach to Jupiter when it passes the orbit of the giant planet in spring 2026. Earlier calculations, based on initial observations and assuming purely gravitational influences, indicated that the comet would pass as close as 53.445 million kilometers from Jupiter, almost exactly matching the boundary of Jupiter's Hill sphere, the region within which the planet's gravity dominates. But comets are not passive objects. They experience non-gravitational acceleration, a force generated by the rocket effect of outgassing as ices sublimate and eject material in a particular direction, slightly altering the comet's trajectory over time. NASA has revised the model describing the relationship between this non-gravitational acceleration and distance from the Sun, now attributing it to the sublimation of carbon dioxide from the object's surface rather than water ice, which vaporizes at a different temperature and distance. This is where Avi Loeb re-enters the story. Loeb has publicly argued that this revised model does not match certain observational data, specifically citing studies based on Hubble Space Telescope images, showing that the object's brightness near perihelion increased much more sharply than the gradual sublimation curve predicted by a carbon dioxide model would suggest. If the brightening was driven solely by CO2 outgassing, which occurs steadily as the comet approaches the Sun, the light curve should show a smooth, predictable increase. But the Hubble data, according to Loeb's interpretation, shows a steeper, more abrupt brightening, which he suggests could indicate a different mechanism at work. Could it be a sudden exposure of a fresh ice reservoir, a structural change in the nucleus, or, as Loeb has hinted, something else entirely that does not fit the standard cometary model? It is important to note that Loeb's interpretation is not universally accepted among astronomers. Many of his colleagues argue that the Hubble data, when properly calibrated and analyzed with error bars, is consistent with a comet exhibiting normal, if somewhat unusual, outgassing behavior. But the debate underscores a fundamental truth. We do not yet have a complete understanding of 3I Atlas. Precise trajectory data will be obtained in March 2026 after astrometric analysis from 3 spacecraft: Juno, currently orbiting Jupiter; JUICE, the European Space Agency mission also en route to the Jovian system; and Psyche, continuing its journey to the asteroid belt. These missions will provide highly accurate positional measurements of the comet from different vantage points, allowing scientists to refine the trajectory and determine exactly how much non-gravitational acceleration is affecting its path. That data will either confirm the carbon dioxide outgassing model or force scientists back to the drawing board. And that is the beauty of the scientific process. Models are tested, refined, and sometimes discarded in favor of better explanations. We are watching that process unfold in real time. At present, 3I Atlas is under continuous monitoring by the International Asteroid Warning Network, operating within the United Nations Planetary Defense Activation Framework. This might sound alarming, but it is actually standard procedure for any object whose trajectory is not yet fully characterized, especially one exhibiting non-gravitational forces. While scientists stress, and I want to emphasize this again, that the comet poses absolutely no threat to Earth, the fact that it is being tracked under the Planetary Defense Protocol reflects the broader commitment to vigilance and preparedness. Astronomers emphasize that attention to interstellar and near-Earth objects remains an essential component of international security, not because 3I Atlas is dangerous, but because the infrastructure we build to study it, the coordination, the observation networks, the rapid response protocols, all of that serves a dual purpose. It advances science, and it keeps us safe. So, where does this leave us? What have we actually learned from this comprehensive briefing, and what mysteries remain? We know with confidence that 3I Atlas is a comet, a natural object composed of ice and dust, not alien technology. We know that it likely originated in a very old planetary system, possibly older than our own, and that it carries chemical signatures distinct from comets born in our solar system. We know that it is behaving mostly like a comet, but with intriguing deviations, unusual chemical ratios, atypical dust properties, spiral structures in its tail, fragmenting nucleus, color shifts, and brightness anomalies. We know that its trajectory is influenced by non-gravitational forces, likely from carbon dioxide outgassing, but that the exact magnitude and nature of those forces are still being debated and will be resolved with more data in 2026. And we know that the international scientific community has mobilized an unprecedented observational campaign, leveraging spacecraft across the solar system to study this rare visitor with every available instrument. But here is what we do not know, and this is where the story gets truly compelling. We do not know precisely where 3I Atlas came from. We can trace its trajectory backward and estimate a general direction, but pinpointing the specific star system of origin is nearly impossible given the vast timescales involved and the chaotic dynamics of stellar motion through the galaxy. We do not know how long it has been traveling through interstellar space. Was it ejected from its home system millions of years ago? Or hundreds of millions? The surface features, once we get close-up images, if that ever becomes possible, might tell us something about its age and history, the cratering from micrometeorite impacts, the erosion from cosmic rays, but for now, that remains speculative. We do not fully understand why its brightness and color are changing in ways that seem inconsistent with simple models of outgassing. Is the nucleus compositionally layered? Are there active vents opening and closing as the comet rotates? Could there be subsurface reservoirs of volatile ices suddenly exposed to sunlight? These are all plausible hypotheses, but we lack the resolution and the continuous monitoring to say for certain. And here is a question I want you to think about, and I genuinely want to hear your thoughts in the comments. If 3I Atlas does come from an older star system, what does that tell us about the diversity of planetary formation across the galaxy? Are the comets and asteroids that formed around ancient, metal-rich stars fundamentally different from those around younger stars like our Sun? And if so, what implications does that have for our understanding of how life-building molecules, the organic compounds and water that comets can deliver to planets, are distributed across the cosmos? Leave a comment below with your take on this, because this is not just about one comet. This is about the broader question of whether the chemistry of life is universal or whether it varies dramatically, depending on where and when a planetary system forms. Tom Statler, during the briefing, offered a closing thought that I think captures the essence of where we are in this investigation. He said, "We're still learning even about what questions we still need to ask, and this, of course, is the scientific process in action. That statement, more than any single data point, tells you everything you need to know about the current state of our understanding. We are not at the end of this story. We are barely past the opening chapter. The data from March 2026, when Juno, JUICE, and Psyche provide their astrometric measurements, will be critical. The continued monitoring by ground-based telescopes and space observatories as 3I Atlas moves through the outer solar system will reveal whether the current anomalies persist or whether they were transient features of its close approach to the Sun. And the theoretical work, the modeling and simulations that scientists are undoubtedly conducting right now will help constrain the possible explanations for what we are seeing. There is also a broader context here that deserves attention. 3I Atlas is only the third confirmed interstellar object we have ever detected, but statistical models suggest that such objects are passing through the inner solar system all the time, perhaps dozens or even hundreds per year, most of them too small or too far away to detect with current instruments. The discovery rate is limited by our observational capabilities, not by the actual population of interstellar visitors. As survey telescopes become more powerful, as automated detection systems improve, as space-based observatories extend our reach, we will find more of these objects. Each one will be a unique data point, a sample of a different stellar environment, a different epoch of galactic history. 3I Atlas is giving us a preview of the science to come, and it is showing us both the promise and the challenges of studying these fleeting messengers from the stars. One of the challenges, as we have seen, is the public communication of science in an age of instant information and viral misinformation. The speculation about alien technology, fueled by a lack of official data during the government shutdown and amplified by high-profile figures on social media, created a narrative that was difficult to counter once it took hold. NASA's response, blunt and backed by comprehensive data, was necessary and appropriate, but it also highlights the importance of timely, transparent communication during the early stages of a discovery. Science thrives on skepticism and debate, but it also requires a foundation of shared facts and rigorous methodology. When that foundation is obscured or delayed, the vacuum is filled by speculation, and separating signal from noise becomes exponentially harder. The involvement of celebrities like Elon Musk and Kim Kardashian in the public discourse around 3I Atlas is frankly a double-edged sword. On one hand, their platforms brought millions of people's attention to an astronomical event they might otherwise have ignored, sparking curiosity and engagement with space science. On the other hand, casual comments and viral posts, especially from individuals without expertise in the field, can spread misconceptions and create unrealistic expectations. The challenge for science communicators, for journalists, for NASA itself, is to harness that attention and channel it toward accurate, nuanced understanding rather than sensationalism. It is not easy, and it is a balance that is constantly being recalibrated in the digital age. Looking ahead, the spring 2026 observations will be pivotal. If the trajectory data from Juno, JUICE, and Psyche confirms the revised carbon dioxide outgassing model, that will be a significant validation of our understanding of cometary behavior and non-gravitational forces. If, however, the data shows discrepancies that cannot be explained by current models, that will open the door to new hypotheses and potentially new physics. Could there be outgassing from the night side of the nucleus, driven by subsurface heat sources? Could the rotation state of the comet be more complex than assumed, with tumbling or precession affecting the distribution of jets? Could there be a population of small, detached fragments traveling with the comet, collectively producing a rocket effect that is difficult to model? These are all questions that the next round of data might help answer, or they might introduce entirely new puzzles. There is also the tantalizing possibility, though it remains remote, that a future mission could be dispatched to intercept and study an interstellar object up close. The European Space Agency has already studied concepts for such a mission, which would require a spacecraft on standby, ready to launch on short notice once a suitable target is identified. The technical challenges are immense. Interstellar objects move fast. Their trajectories are difficult to predict in advance, and the launch windows are narrow. But the scientific payoff would be extraordinary. Imagine a spacecraft equipped with cameras, spectrometers, and sample return capabilities, rendezvousing with an object like 3I Atlas, capturing high-resolution images of its nucleus, analyzing its composition in situ, perhaps even collecting fragments of ice and dust to bring back to Earth. That would transform our understanding of interstellar chemistry and planetary formation in ways that remote observations, no matter how sophisticated, simply cannot achieve. So here is where we stand as of today. 3I Atlas, the interstellar comet that captivated the public imagination and sparked wild speculation during a government shutdown, is exactly what NASA says it is: a comet from another star system carrying the chemical fingerprints of an ancient stellar environment, behaving in ways that are mostly expected but occasionally surprising, and posing absolutely no threat to Earth. The data released in last week's briefing represents the most comprehensive observational campaign ever mounted for an interstellar object, a testament to international collaboration and scientific rigor. But the data also reveals how much we still do not know, how many questions remain unanswered, and how provisional our understanding of these rare visitors truly is. The next critical milestone will come in March 2026, when spacecraft near Jupiter provide the trajectory measurements needed to resolve the debate over non-gravitational forces. Until then, 3I Atlas continues its journey outward, monitored by a global network of telescopes and spacecraft, a frozen messenger from the deep past of the galaxy, reminding us that the universe is vast, old, and full of wonders we are only beginning to comprehend. The scientific process is in action, and we are watching it unfold in real time, with all its uncertainties, debates, and moments of revelation. That is the story of 3I Atlas, and it is far